Yeah, in my last class I told you what is power electronics and goal of power electronics. Okay. Now, what is the definition of power electronics? Power electronics is the technology associated with efficient conversion and control of electric power by power semiconductor devices. Okay. That is the definition of power electronics. And what is the goal of power electronics? It is to control the flow of energy from electric source to electric load. I have been telling that power electronics is very popular. It is being compared with computers. It has been said that it is a enabling technology for distributed power generation. So, if it is so popular, it has to be very efficient. In the sense, power electronic equipment should have very high efficiency. It should be highly reliable. Cost, size and weight should be as low as possible. Okay. So, definitely computer power supply is so light, that should be a power electronic equipment. Fan regulator so small compared to the conventional resistor type. Definitely this is a power electronic equipment. Okay. It is small, highly efficient. Okay. Cost wise, maybe this is definitely higher than the conventional regulator. The conventional regulator, I was told that cost about 60 rupees, and a good regulator, a power electronic regulator costs around 100 rupees or so. So, maybe this equipment costs around 50% more than the conventional resistor type regulator. So, while evaluating the cost, you need to find out the payback period. This is not the initial cost. You may be able to pay more in the beginning. The question that should be asked is how fast you can recover that cost, the so called the payback period. Highly efficient, there is no power loss here, or power loss is very small, that is why it is so small, is mounted inside the switchboard. Whereas the conventional fan regulator with the resistor type, there is power dissipation, so energy is being lost there. So, definitely the power consumed, the total power consumed by the fan and the regulator is high. So, therefore, you have to, or electricity bill is high. So, you need to find out, or one has to determine the payback period rather than the initial cost. Okay. So, definitely this is a power electronic equipment, whereas the regulated power supply that we are using in the lab, it is so bulky, so heavy, is not a power electronic equipment. But then both of them are doing the same thing. Regulated power supply also gives you plus or minus 5 or 12 depending upon the voltage rating. Even the computer power supply, it gives plus 5, minus 5, plus 12 and minus 12. Both of them are doing this almost the same function. So, why it is so compact and why it is so heavy? We will see. See, in other words, see here there is a question, how can the circuit change the voltage level yet dissipate low power? Input to both the regulators is a single phase AC. Okay. So, why the one circuit consumes or dissipates less power compared to the other? See, now all of us know the circuit elements are resistor L and C, they are considered to be passive elements, and transistors, MOSFETs, they are considered to be active. There are other active elements also, I will tell you sometime later. At least BJT or transistor or MOSFET you would have studied by now. In the passive elements, resistor consumes power, whereas L and C, they do not consume power. Okay. Now how about the active elements? Okay. See in this circuit, okay, I have a NPN transistor. Okay. Now what is the power loss that is taking place in the device when it is on? Okay. It is the collector current IC into VCE is the power that is dissipated here, power loss. Okay. So power loss in the BJT is VC into IC, and we all know that if I operate this transistor in active region, VCE is high, okay, and as if the transistor is operated in saturation, VCE is low. Okay. So the power loss in a transistor can be reduced if I operate it in saturation. So in that case, VCE is actually VCE sat. See, for a small signal transistor, the teacher would have told you it is as low as 0.2 volts. Okay. But then this voltage increases as the current rating also increases. We will see sometime later. Okay. So VC sat into IC is very low. So therefore, if I operate the device in saturation, or if I operate the transistor in saturation, I can reduce the power that is dissipated in the transistor. So what are the conclusion that I can make? In a power electronic equipment, I should be using, or we need to use only L and C, okay, and the active devices, say for example, if I am using a transistor, we should operate it in saturation. Okay. So if I use resistor, or if I use any active element and operate it in active region, okay, there is going to be a power loss. Okay. So see, here is the conclusions. Resistor and active elements operated in the active region, either MOS or a BJT, they result in power dissipation. So therefore, in order to achieve high efficiency, active elements should be operated either in saturation, okay, or in cutoff. When there is cutoff, there is no current, again the power loss is 0 approximately. In addition, you use only L and C elements. Okay. I will just give an example. Take for example, input is 30 volts and output voltage is 5 volt DC. That is required. I have an input 30 volts, the circuit requires 5 volt DC. How do I get this 5 volts? I have considered 3 different ways. One is what we studied in a basic circuit theory, use of potential divider. Okay. Use a potential divider and I can get the required output voltage. Okay. So the moment I use a potential divider, which is nothing but a resistor, there is going to be a power loss, I square R loss. Okay. See here, this is the circuit. Input VDC, I have connected R, you vary this R and this R here such that you get a required voltage, required output voltage. Second case is I will use a transistor, connect it in series, okay. Input is 30, output I require is 5 volts. Somehow I have to operate the transistor in such a way that voltage across it is 25 volts. Okay, this circuit is something like this. Input 30, output that I want is 5. The remaining 25 volts should drop here across the BJT. So 25 into whatever the current that is flowing in the load is the power dissipated in the transistor. Okay. Now what could be the third option? See, for some time I close the switch to position 1, okay, and for some time I will close the switch in position 2. Okay. I am not going to discuss the various parts of this circuit, that we will be discussing sometime later in the course. And so this is the voltage that is being applied. When I am closing to switch 1, it is a VDC, and when I am closing the switch in position 2, it is 0. Okay. Now what is the average value of this voltage? When it is 1, for t1 seconds it is VDC, the switch in position 2 for t2, and that the voltage applied is 0. Now the average value of this voltage is VDC into t1 divided by t1 plus t2. Okay. Now while depending upon VDC and the required value of V0, I will adjust t1. Okay. Since this active device, the switch, is operated in saturation, okay, power loss across it is approximately 0. Okay. So thereby increasing the efficiency. I am here applying, or I am controlling the switch such a way that average value is controlled to a required value. So this is the principle that is being used in the power electronic equipment. Okay. Now to summarize the application of power electronics, okay, to be very frank, power electronics is used in almost all the equipments, or wherever efficient power conversion that is required. There is no way out. There is no way out. So I have just listed few applications, very few. Major application is in motor drives. Motor drives, to control the speed or to vary the speed over a wide range, because almost all the machine, separate like excited DC machine, induction machine, constant speed motors, the application requires a wide variation in speed. You have to use a power electronic converter. Power supplies, okay, a regulated or a power supply that is used in a computer, a UPS, the UPS that is used in a home. The moment the AC power supply goes there has to be, or there is an equipment which provides us AC supply again. Lighting, especially when the input voltage is very low, the conventional ballast won't work. Okay. There is a voltage range for the conventional choke or a ballast in a fluorescent lamp. If the input voltage falls below a certain value, it will not glow. Whereas if I use an electronic ballast, it can operate it even at a very low voltage, very low input voltage. The fourth one, high frequency induction heating. Okay. Electric welding, active filters. What is active filter? In the sense, if there are harmonics in the supply, you need to filter them. Okay. So you require power electronics there. In transmission line voltage support, to provide reactive wars, to increase the power transmission capability, to transmit the bulk power, that is nothing less HVDC, electric vehicles, to process the power from a non-conventional source. I told you that power electronics is an enabling technology for distributed generation, or without power electronics it will be extremely difficult to generate power from non-conventional sources. Okay. These are very few applications. Okay. Now, what is the reason for the progress in power electronics? The progress in power electronics is primarily due to the advances in power semiconductor devices. Advances in power electronic devices. I'll just show you some of them. A small diode, 0.5 amperes, it can carry, the rating is 0.5 amperes. It can block say 50 volts or so. High power diode can carry 40 amperes and it can withstand 1200 volts. See, if I use a diode in a AC supply in the negative half cycle, okay, diode may get reverse bias, diode gets reverse bias, and it has to block or withstand the voltage, whatever the input voltage. So this diode can block a voltage up to 1200 volts. Okay. A small BJT, a transistor NPN SL100 can carry, a rating is 500 milliamperes and can be used in a circuit, or it can block up to 50 volts. See the power transistor. This was mounted on the rear side of the power supply, regulated power supply. Yesterday I showed you. Okay. A single phase diode bridge. Single phase diode bridge. See, here there are single phase diode bridge is nothing but this one. This is a single phase diode bridge, 4 diodes. input, I need to connect, these are the two terminals and these are the two plus and minus. One of them could be plus and minus, these are the two input, a single phase diode bridge. Okay. A small transistor, 500 milliamperes, 50 volts. Okay. Very common, maybe is used in the lab. One module, see here, there are two such devices, a switch, okay, which can be controlled using a gate signal or a base drive, if it is a BJT, this switch, and a diode that is connected across it. Why it is, we will see later. So there are inside, we have two such devices and two diodes, anti-parallel diodes. Okay. Each device can carry 50 amperes, each device can carry 50 amperes, and it can block as high as 1200 volts. See, these three terminals 1, 2, 3 corresponds to these three 1, 2, 3. These three are the terminals. And see, there are two terminals here. The control signal, the base drive is to be connected between these two. Base drive between these two. Similarly, for this switch, these are the two terminals. Okay. This is one leg. Now, see, there are dedicated chips to supply the required base drive to this transistor. You don't have to use a separate discrete components to feed or to supply the gate drive for this device. Okay, here is a dedicated chip, all the components are inside, dedicated chip, which can be, there are various pins have been brought out, okay, and it can be directly fed, or outputs can be directly connected to these two pins, and you can operate one such device. To operate both of them, you require two such dedicated chips. Okay. See, now the very recent power module, what it is, see, here is it. There are three such legs. If I consider this is one leg, there are three such legs here, three such legs. Okay. Each device can carry again 75 amperes and it can block 1200 volts. The rating, there are 6 such devices integrated. I said you require a separate dedicated supply, or you need to have a separate driver circuit to supply the required gate drive for this transistor. So this is the dedicated chip that is used to drive this. You can design your own circuit using various discrete components, transistors, small resistors, and op amps. Okay. Whereas this circuit has built-in the driver circuit, what is known as the intelligent power modules. The protection part is also integrated here. Protection in the sense, in case current is higher than the required or higher than the rated value, automatically the gate drive is blocked. Intelligent power modules, the protection is built in. Okay. Whereas here, if you are designing your circuit, one has to design your own protection circuit to protect this device, whereas the protection is built in here. Okay. A small 500 milliampere transistor, 75, okay, in between another power transistor that is used in a regulated power supply, one such leg wherein there are two controllable switches, two diodes, each of 75 amperes, 1200 volts. See the size, see the reduction in size. Here I have to use my own external driver circuit and a protection circuit. All 6 such devices, protection is built in here. See, there is another very high power device, again a controllable device, can carry 300 amperes of current, can block again 1200 volts. See, two sides, now it requires two heat sinks, it is some sort of a sandwich type. Again you require one more heat sink on top of it. So now you can yourself see the progress in a power semiconductor technology. A small transistor, relatively higher, two 75 ampere devices, 6 75 ampere devices. Again there are 6 diodes, anti-parallel diodes. Here there are 2 anti-parallel diodes. A 300 ampere device, dedicated IC, a dedicated circuit which provides the gate drive for the controllable switch. Okay. So the progress in power electronics is primarily due to the advances in power semiconductor devices. Apart from the power semiconductor devices, it is the fast processors. Okay. So digital DSP, digital signal processors, dedicated chips, various circuit configurations. What exactly are the various circuit configurations, I will discuss in the course. Then there came various control and estimation techniques and materials. I will just give another example. See how small a current sensor, okay, works similar to a current transformer. The rating is 50 ampere turns. In the sense I have put only one turn here, so I can supply as high as 50 amperes of current through this. Okay. What do I need to do? There are 3 pins, plus 15 volts, minus 15 volts, and a small resistor, what is similar to a CT burden. Okay. See how compact it is. 50 ampere turns, total ampere turns, require plus 15, minus 15, and a small resistor, what is known as equivalent to a burden. Excellent linear characteristics, very good response. Bandwidth is 0 to 200 kilohertz. a current sensor. So, all these factors are responsible for progress in power electronics. Again, let me tell you, I will show all this, the power semiconductor modules at the appropriate time during the course. Okay. Now, what are the significant events in the past history of power electronics? See, I will show you. In 1783, the concept of semiconductor came in by Volta. In 1830, rectification effect of copper oxide was identified, was invented or observed. 1876, selenium rectifier. 1896, the single phase bridge rectifier circuit, and 1897, it is three phase bridge rectifier circuit. I will just show you what is single phase bridge rectifier and three phase bridge rectifier. It is simple. See here, a single phase bridge rectifier, okay, something like this, single phase bridge rectifier, diode rectifier, okay, single phase, phase and neutral. Here a three phase, three such legs. See, the beauty of this circuit is was invented in 1897. It is almost 100 years and still it is very popular. Okay. It's more than 100 years this circuit was invented and still it is being used extensively. Okay. And in 1901, invention of glass bulb mercury arc rectifier was invented. Okay. And next major event was 1948, invention of transistor. Okay. It is a major step, a major invention in the history of power electronics. In 1953, germanium power diode was found. And in 1954, silicon power diode. Okay. And in 1957, SCR, a silicon controlled rectifier. In 1985, it was invented. Okay. So, in 1957, SCR was invented. It could block around 500 volts. And today, SCR, which can block a voltage of 6.5 kV, 6.5 kV. What is exactly the SCR, the characteristics, I'll tell you. Okay. So, the invention of SCR, it gave a major thrust in power electronics. Okay. So, that is about the significant events in the history of power electronics, and that completes my lecture on introductory lecture on power electronics. Okay. Now we will go into power semiconductor devices. What are the devices that are being used in power electronic circuits? Okay. Power semiconductor devices, it is said that they are the heart and soul of modern power electronic equipment. Power semiconductor devices are heart and soul of modern power electronic equipments. these are used as switches. Okay. All of us know what exactly is a switch. Okay. So what are the ideal properties of the switch? See, here is a circuit, a single line diagram, okay, and if this arrow shows that to close the switch, I need to change in this. So what are the properties of this switch? When the switch is off, IS should be 0. Okay, there should not be any current flowing through the switch when it is open, okay. And it should be able to withstand any voltage across it. Okay. In other words, this switch should be able to withstand any voltage varying from minus infinity to plus infinity. Okay. And when it is on, what should happen? The voltage across it should be 0, and it is capable of passing any current through it. Okay. So when it is open, 0 current, any voltage, and when it is closed, 0 voltage, any current. Okay. So what happens now? Now power that is dissipated in the switch, when it is on or off, it is 0, because when it is off, current through it is 0. So power dissipated is 0, and when it is on, voltage across it is 0. It can pass any current. So power dissipated is 0. Therefore, when the switch is conducting or it is blocking, in other words it is open, the conduction loss and the blocking loss should be 0. They will be 0. These are the characteristics of an ideal switch. What about the other characteristics of the ideal switch? Switch should be turned on or off instantaneously. Okay. See here in the circuit, I will just explain to you. I have a load, some voltage here, and I have to control the voltage applied to the load. So I should be able to close the switch instantaneously or open the switch instantaneously. So what is the transition? When I close the switch, voltage across it is 0, and when I open the switch, whatever that is voltage that is being applied here will appear. So this transition should be instantaneous. So similarly, when it is open, current is 0, so in this period, and at this point it is turned on. Okay, this current, depending upon the load, transition from 0 to this current should be instantaneous. So what is the consequence? If the changeover is instantaneous, time taken or T on, that is equal to T off, both are 0. So therefore, the loss that is taking place during on time and when it is being turned off is 0. I will repeat, the transition from off state to on state is instantaneous. So therefore, the turn on loss, okay, is 0. Similarly, from on state to off state again it is instantaneous. The loss again during turn off process is 0. So, these are nothing but the switching losses, the losses that are taking place during switching, they are 0. So, an ideal switch should have 0 conduction losses, 0 blocking losses and 0 switching losses. Okay. So, if I plot the device characteristics in xy plane, in vi plane, sorry, off state, any voltage it should be able to block, any voltage plus infinity to minus infinity, and when it is on it should be able to carry any current. This is the locus. Okay. How about the practical devices? Can you have these ideal characteristics in practice? Answer is no. It's rather impossible to get these ideal characteristics. But then there should not be much difference between the ideal characteristics and a non-ideal characteristics, or an ideal switch and a non-ideal switch. See, efficiency of an ideal transformer is 100%, there are no losses at all. But then efficiency of a good transformer is of the order of say 98% or so. So, you cannot have a large difference between an ideal switch and a non-ideal switch. Okay. So, in a non-ideal switch, off state, when the switch is open, current is non-zero, a small current flows. What it is, we will see. And when it is off, it cannot block any voltage, that is its voltage rating. You cannot exceed that voltage. For example, any switch that is used to control the incandescent bulb, or a circuit breaker, a miniature circuit breaker MCB that is used in our home in the main switch, each of them have a voltage rating. So, similarly, a semiconductor switch, it has a voltage rating above which it will fail. Also, when the switch is on, voltage across it is non-zero, and again there is a maximum current carrying capability. You cannot exceed it. So, off state current is non-zero, so there is going to be losses when the device is blocking or when the device is off. When the device is on, voltage across it is non-zero, there will be a conduction losses. So, therefore, both blocking as well as conduction losses are finite. Again, transition from on state to off state is not going to be instantaneous. See here, in current could follow this path. Okay, current slowly falls, and this is the voltage across the device or the switch. Okay, is not instantaneous. So, there is going to be a finite losses during switching. So, therefore, the locus in the VI plane is not going to be along the x axis and along the y axis. there are limits. I had showed you there are 6 devices here, or 3 such legs, each of 75 ampere and 1200 volts it can block. But then each device at any given time will not be able to carry 75 amperes and voltage across it is 1200 volts. No. There is something known as the maximum power that it can dissipate. There is, all the devices are, in other words, all the devices are thermally unstable, because at any given time power loss that is taking place is voltage across it into the current that is flowing through it. Because as the power loss increases in the device, the junction temperature will increase, and if it exceeds a certain value it will fail, what is known as the thermal limit or the power limit. Okay. So each device has something known as the safe operating area. At any given time the operating point should lie within the safe operating area, SOA zone. One such area is shown here. I limit, maximum current it can carry till a voltage range. So you cannot it cannot pass 75 amperes at 1200 volts, it's just not possible. So there is a limit. I limit till a certain range. So this is the voltage. The voltage across it could be 1200 volts, but then current should be within this limit. See, this is the limit, and this is the power limit. I have just shown here voltage limit, I limit and the power limit. There could be other zones also. So depending upon, see, we will be discussing various devices, and for each device we will discuss what is the safe operating area. Okay. So I told you that each device is thermally unstable because power dissipated is non-zero during conduction period, during switching and also during blocking mode. So therefore power dissipated is non-zero, there is going to be a temperature rise, so heat has to be dissipated. So you need to know, or one has to calculate the heat sink requirement or the cooling requirement. Okay. And there are various types of heat sinks, and maybe if you observe in the power supply that I showed in the computer, there is a small fan inside to dissipate or to maintain the temperature within the limits. So it all depends on the cooling requirement, depends on the losses that are taking place. Okay. फास्ट जा रहे हैं क्या? Yeah. Yeah, that's about the characteristics of an ideal switch and a non-ideal switch. Now, what are the various types of switches that are used in power electronics? One is the uncontrolled switch. Why it is known as uncontrolled switch? It is known as uncontrolled switch because on and off is determined by the circuit in which the device is connected. I will repeat. The on and off is determined by the state of the circuit in which the device is connected. Okay. I will give an example. See here, an uncontrolled switch, a diode is an uncontrolled switch. Why it is uncontrolled? Take this circuit, a 10 volts DC power supply, I have connected a diode, okay, and a 10 ohm resistor. What is the current that is flowing? Assuming that voltage across the diode is around 0.7 volts, so current is approximately 10 minus the drop across it divided by the load resistance, okay, approximately. I am neglecting the on state resistance of the diode, okay, I am just saying this drop remains constant. Okay. Now, instead of having a DC supply, if I had a AC power source, AC source, what would happen? At the positive zero crossing, this diode would have started conducting. Okay. For time being, I am neglecting the voltage across the diode. So, if I had a AC here and a resistive load, at the positive zero crossing, diode starts conducting, okay, and at the negative zero crossing, diode turns off. So, therefore, the on and off of this diode is determined by the circuit here and not by, you cannot determine externally, or you cannot decide externally as to when this diode should turn on or when it should diode turn off. The circuit decides. That is why it is known as an uncontrolled switch. It has only two elements, two terminal device, anode and cathode. Okay. What is another type of switch? It is a semi-controlled switch. Why it is semi-controlled switch? It is because switch may be turned to one of its state. Okay. I am telling you, switch may be turned to one of its state using a control terminal, and other state is reachable through the circuit only. See, in the previous circuit, diode, both the circuits on as well as off, it is completely determined by the circuit itself. But in the case of a semi-controlled switch, again it is a three terminal device. Okay. SCR could be one of the examples here. See here, what is XCR? I will tell you later. Okay. You can turn on this device by supplying a positive gate current. Okay. When the device is forward biased, and supplying some gate current, you can turn this device on. Okay. Having turned on the device, you cannot turn it off using gate. See, I will repeat. When the device is forward biased, by supplying a positive gate current, thyristor or SCR can be turned on. But then having turned on the device, you cannot turn it off using the gate. So, hence the name semi-controlled switch. What about the third type? See, there is a totally uncontrolled, a semi-controlled, the third is a fully controlled switch. It is very obvious, both on and off should be possible using the control element, control terminal. So, take for example a BJT, I can turn it on by supplying a positive base current, I can turn it off by making the base current 0. Okay. So, diode is an uncontrolled element, uncontrolled switch, because whether it is on or off is completely decided by the circuit. SCR is a 3 element device. It can be turned on only by supplying a positive gate current, and it should be forward biased. You cannot turn it off using gate. And the third one, what is known as a fully controlled switch, a controlled switch, wherein the device can be turned on or off by using a control terminal. Okay. So, more about it we will study in our next class. Thank you.